Good afternoon, ladies and gentlemen. Welcome to the session of the Nečas and Mechanics. So today's speaker is Chiara Gavioli from the Czech Technical University. So Chiara got her PhD at the University of Modena in 2021. I think her PhD advisor was Michele Eluteri, and she received the Gavioli Prize for her thesis. Then she moved to the Technical University of Vienna, where she worked in the group of Gavioli till January this year, and from February she is at the Czech Technical University, Faculty of Civil Engineering, Department of Mathematics, as a Marie Curie Fellow, and her advisor here is publication. So Chiara is an expert in PDEs, in particular PDEs with hysteresis operators, and I think from this topic we should talk today. So, thanks for coming.
Thank you very much, Martin, for the introduction.
Okay.
Thank you. Today I will present some slightly not really recent results, but that we're still working on, or we plan to work on during my fellowship here in Prague. And this was a joint work with Bettina Detman from the University of Duisburg-Essen, and with Pavel Krejci, Jan Lamač, and Julia Namlieva also from the Czech Technical University here in Prague. And before I start with the mathematical model, I will tell you something about what line consolidation is, because this is something that belongs to civil engineering, so you may maybe not really familiar with it. And the motivation is a practical problem, so a real world problem in civil engineering, which is that of stone weathering. And weathering is the aging of the stone due to the weather. So the situation that you should have in mind is that, for example, of a historic building, which is subject to aging due to pollution, to the freezing and melting cycles of water inside the pores. And this, of course, produces damages in the stone. And so the civil engineers would like to prevent this from happening. And there have been many attempts to solve this problem. One of the attempts was by using a water repellent treatment and put it on the outside layer of the stone. But this in the end resulted in even more damage because it created a kind of hard layer on the outer surface. And this has produced even more damages than the weathering. And so they looked for other kind of solutions, and another possibility is given by this consolidation. That is what I will be going to talk about. And the consolidation approach is different from the other one also in the underlying philosophy, let's say, because the water repellent treatment is more towards the preservation philosophy. So you want to totally preserve the stone in whatever state of weathering it has reached and stop any future decay. While with the consolidation, you still allow the stone to be ruined, to be damaged by the weather, but at a slower rate. And the favorite treatments by the civil engineers are those that do not alter too much the characteristics of the underlying stone. And some characteristics are more important than others, like, for example, the strength or the thermal dilation, and also the color, because if we are speaking of historic building, also the color of the stone is important. It should be preserved as well. And among all the possible consolidants, the lime water is one of the best because it is reversible and it is also very simple to use, as I am going to explain. Okay, how this works: you take this water lime mixture and you let it penetrate inside the pores of the stone. And this lime is calcium hydroxide plus some impurities. And what happens at this stage is that the water of the water lime mixture evaporates, while the lime particles remain inside the stone, and they react with the CO2 that it is inside the air in the pores. And this chemical reaction produces the calcium carbonate, which is our consolidant, plus some water. And the calcium carbonate is not water soluble, so it remains inside the stone and it glues the particles together. And to give you a better idea of what it looks like, these are two pictures taken from the engineering literature. In the first picture, you can see the consolidation at an earlier stage, while here, the consolidation at a later stage. And this Portlandite is the natural form, so the form that you can find in nature of the calcium hydroxide, while this calcite and laterite are two polymers, so two different crystal forms of the calcium carbonate. So here you see that at an earlier stage, we still have some calcium hydroxide, and moreover, also the structures look more like, I don't know, like powder. While at a later stage, you can see that this crystal growth has happened, and this is what really gives the strengthening effect in the stone. So there is a change in the porosity, and the structure is reinforced. And of course, this is a well-known technique for the civil engineers. It has been known for centuries already. So they have a lot of data, but of course, no mathematical model. At least before that, we provided our model, and yeah, so it will be important for them to have a mathematical model also to optimize the procedure, because it has a lot of defects. It is good for the reasons that I told you before, but it has some drawbacks. Like, for example, it is a very slow process. Just these two pictures. The first one is taken after 1 month, and the second one after 6 months. And you see in this paper, it's about accelerating carbonation. So at the natural rate, it would be even slower. So this is a very slow process. And moreover, they need to repeat it many times because the consolidating layer that is formed after with the carbonation process is very, very thin. And so there is some space for improvements, let's say. This is why we decided to study this problem. Also, this resulted after a discussion of Pavel with the civil engineers at the Institute of Theoretical and Applied Mechanics of the Czech Academy of Sciences. So this was brought to our attention by them, actually. Okay. So now I start with the mathematical model, how we derived it. So the setting, our stone that has to be consolidated is modeled as a porous medium. I reported here the chemical reaction. So we let the calcium hydroxide penetrate into the pores, and this reacts with the CO2 and produces the calcium carbonate. And the first ingredient that we need for our model is the mass balance for the chemical reaction, which essentially tells us that for each of the elements, this ratio, the one between the mass source rate and the molar mass, has to be constant for each of the 4 substances. And of course, for the calcium hydroxide, for the CO2, have a minus sign because these 2 elements are being consumed during the chemical reactions. Okay, then we have the mass balance for both the water and for the calcium hydroxide. So here we have this rho W is the density of water, and this C dot is the mass source rate of water produced by the chemical reaction. So this is a control volume. So this source rate, okay, this is the source rate of the water. This represents essentially this integral, the amount of water which is contained into the control volume V. So this is the variation over time of the amount of water inside the control volume V. And so the difference between these two terms gives the exchange through the boundary of the control volume. So this is standard mass balance. And the same for the calcium hydroxide, where now, of course, we have the rho H is the density of calcium hydroxide and so on. Everything is changed accordingly. Okay, then we can rewrite them in differential form with the divergence theorem, and now we need to specify the fluxes, so how the fluxes look like. And for the water mass flux, we assume that it obeys the Darcy law, which is a popular law for the filtration in porous media. And we essentially say that the flux of water is proportional, is opposite to the gradient of the capillary pressure. P is the capillary pressure. And then we make this assumption on the permeability function. We assume that it is, first of all, a function of the amount of calcium carbonate, and that it is non-increasing. And this is a physically reasonable assumption because the permeability essentially measures the willingness of the porous medium to let the liquid flow. So here we are saying that essentially as the amount of calcium carbonate increases, this willingness is decreasing. This, of course, because of the consolidating effect. So the calcium carbonate is depositing on the surface, and so the permeability decreases. Okay, and then we have the assumptions for the flux of calcium hydroxide, and we assume that it is made of two different terms, one accounting for transport and the other one for diffusion. And for the transport velocity, we assume that it has this form, so it's proportional to the water flux through this convolution term. And okay, this is made mainly for mathematical reasons that I will show you later to derive our estimates. But we believe that it is anyway reasonable to assume that the velocity in a point x depends on the flux in a neighborhood of the point instead of really only on the point itself. So we believe it is still reasonable that the velocity has this form. And okay, of course, then we multiply by h, because if h is equal to 0, this means that we have no calcium hydroxide, so we have nothing to let into the pores. And then we have the diffusion term here, the gradient of the concentration. And again, if S is equal to 0, so if we have no water, because S represents the amount of water, then of course we cannot have any diffusion of the calcium hydroxide. Okay, so these are the equations that we have up to now. And one can see that there are still two relations missing, so we have still too many unknowns. And the relationship that we still need are, of course, a kind of constitutive relation between the capillary pressure and the saturation. So S is the amount of water inside the pores. If S is equal to 0, we have no water. If S is equal to 1, they're completely saturated. And we assume that there is a functional relation of this type. So at P is equal to F of S with that increasing function. And then the second law that we need is the so-called law of mass action, which is a famous law in chemistry, which essentially tells us that the rate of the chemical reaction is proportional to the product of the concentrations of the reactants. But what does this mean? Well, this gamma is a constant, is the speed of the chemical reaction, essentially. But then, what is this law telling us? Well, this essentially tells us that if H is equal to 0, or if S is equal to 0, or if S is equal to 1, then we have no chemical reaction. But H equal to 0 means that we have no calcium hydroxide, so of course we have no chemical reaction. S equal to 0 means that we have no water, so again, no chemical reaction. And S equal to 1 means that the pores are completely saturated, so there is no air, and of course no CO2. And so again, if S is equal to 1, we have no chemical reaction. So this is essentially the meaning of this law of mass action. Okay, and then we need, of course, some boundary conditions. And for the normal flux of water, we assume that it is proportional to the capillary pressure inside and outside the body. So this alpha is the permeability, the boundary permeability of water. While for the normal flux of calcium hydroxide, we assume, well, first that it can point only inward. So this is the meaning of the positive part, proportional to the difference of concentrations between the inside and the outside. And also that flux happens only if the outer concentration is bigger than the inner concentration. And this is exactly, yeah, this models what I was telling you before, that after you let the water lime solution penetrate inside the pores, the water is removed by evaporation while the lime particles remain inside. And so this is exactly the meaning of this boundary condition. The lime particles cannot go outside, they stay inside, and so this is when we impose this with the positive part. Okay, so this is our system in weak form. So we have the mass balance for water, where here we have inserted the expression for the flux, so the Darcy law, and of course the boundary condition. And here we have the mass balance of calcium hydroxide, where again we have inserted the expression of the flux given by both diffusion and transport terms. And again, this unilateral boundary condition. And here at the right-hand side, we have, here is where the mass source terms are, and this is given by the law of mass action. The plus, because the water is produced by the chemical reaction, and here is the minus, because the calcium hydroxide is consumed by the chemical reaction. Okay, then we have some initial conditions, and of course the aim is to prove that this system has a solution. And the main difficulties are that, as you can see, there is a strong nonlinear coupling between the two unknowns, S and H. And this is hidden also in this term here, because this V was the convolution term with the water mass flux, and water mass flux is this one. So it's proportional to the gradient of S. So we have this nonlinear coupling also here. And then, of course, we have this, also the non-standard boundary condition, let's say. This is another challenge. Okay, so this is our existence theorem. So we assume essentially that on the boundary data and on the initial data for the saturation, that they are bounded between 0 and 1, which is the physically admissible range. And also for the initial concentration of calcium hydroxide, and or for the concentration on the boundary, we assume that it has to be greater than 0 and smaller than some H flat. Okay, then we have some assumptions on the functions that appear in the model. So F was the function relating the capillary pressure to the water saturation. And we assume, as I said, that it is an increasing function, and its derivative is bounded between two constants. K was the permeability, and we assume that it is continuously differentiable, and again, bounded and increasing. Yes, it was a crucial assumption. It is an increasing function of the amount of calcium carbonate. And then we have sigma, which is a continuous function with contact support, and some assumptions for the permeabilities of water and of calcium hydroxide on the boundary. And this is what we can prove. We prove that the system has a solution, a couple SH, which has the following regularity. So for S, we essentially get what we expect. So I'm derivative in L2 and gradient of S in L infinity L2. While H is a bit more delicate because, okay, we get the gradient is in L2, but for the time derivative, we get it is only a distribution, it's in W minus 1, 2. And what we can prove additionally is that the saturation is bounded between 0 and 1, and the concentration of calcium hydroxide is positive. So again, we have a solution that it is physical. So we can prove that it is really in the physically admissible range. And how the proof of existence goes? Well, we first cut off the nonlinearities. So this QR is essentially the projection on the interval 0R. So we are cutting off the functions where they are too big. And for the regularized system, the maximum principle holds. So we can prove that if the value of the saturation and of the concentration of calcium hydroxide are bounded, then almost the same, let's say, holds for the value of the saturation and the concentration almost everywhere in space and time. I say that almost the same holds because for H, we can only prove with the maximum principle that it is non-negative. While the upper bound is more delicate, we cannot get it immediately, essentially due to this unilateral boundary condition. This is what prevents us from getting also the upper bound immediately for H from the maximum principle. And for that, so we need to do a bit of work. And the same for V, because once we prove that H and V are bounded, then the solution, we can choose the cutoff big enough in such a way that the solution to the cutoff system is a solution to the original system. Okay, in order to prove the boundedness of H and V, we need to do some work. So we first prove some preliminary estimates, which are quite simple to derive. The first one is obtained by testing the H equation by 1. So in such a way that, okay, this term disappears, of course. This term, we can prove that it stays bounded because if H is bigger than the outer H, then this is 0. Otherwise, if it is smaller, then it is also smaller than H flat, which was an upper bound for H, for the outer H, and so this stays bounded. Well, this is negative. And so in the end, we get an L1 estimate for H. Okay, once we have that, we can obtain a W12 estimate for S. And this is obtained by testing the S equation by S. And for this theory, what is it here? We exploit the L1 estimate that we have just derived. Okay, so preliminary estimates are L infinity L1 estimate for H and W12 estimate for S. And once we have this, now it's time to try to deduce an upper bound for H, which was not immediately available from the, sorry, for V first. And by definition, this is really by definition because V was defined as the convolution, essentially with the gradient of S. So this is what we obtain for the L infinity norm of V. So then we need to estimate the L infinity L2 norm of the gradient of S. And this is done by testing the S equation by Fs of t. And here again, this term is bounded by using the W12 estimate that we obtained before. And so in the end, by using some Young's inequality here, we obtain that the L infinity L2 norm of the gradient of S is bounded by the L2 norm of H. And so now the problem is to estimate the L2 norm of H. So we are moving the problem. And to estimate the L2 norm of H, this is quite maybe the most delicate step of the whole existence proof. We need to test the equation, the H equation by H. And okay, so this again, if H is smaller than, if H is bigger than H outside, then this is 0, otherwise it's bounded by H flat, so it's not a problem. And the same here again, this term is negative, so what is left to estimate is the nonlinear coupling between H, gradient of S, and gradient of H. But here is where this additional, let's say, regularization through the convolution for the velocity really plays a role, because at this point, since this V is essentially, okay, this is exactly the estimate that we have because the truncation of V is of course smaller than V itself. So since we already have, let's say, an integral over omega, we can push it out of the integral here. And at this point, we can apply some Poynter's inequality for H and the gradient of H. And so this is what we obtain. And this is the key point, because here we really need to play with the exponents and with the interpolation inequalities. And what we use here is specifically some Gallardo-Nirenberg inequality. And in the end, what we get is this, with an exponent 49/50, which what we aimed at was getting an exponent smaller than 1, and so we are safe. And yeah, this is essentially obtained by using again this estimate for the gradient of S, and then by using the Goyard-Bonnier-Berlin equality, we essentially estimate the L2 norm with respect to the L1 norm, because we already had the estimate for the L1 norm from the basic estimates that I showed you before. Okay, so once we have this estimate for the gradient of H, here was for the norm of H in an infinite L2, we have the bound in L2, and again, a bound for the gradient of S in an infinite L2, and we can come back and in the end, we obtain an L infinity bound on the velocity. And of course, all this is independent on the truncation parameter R. Okay, and then what is left is obtaining an infinity bound also for the function H, because it was, I say it again, it was not available immediately from the maximum principle. And this is done by Moser iterations. Essentially, we test by a power of the function H, not really by a power, but by a cutoff of the H2, the 2n plus 1, because of course we need to have an admissible test function, so we cut off the function. But okay, I will not give you the details of this because it's very technical, but it's kind of Moser iterations, and in the end we get an estimate in L infinity for the H. Okay, but at this point, if we choose the truncation parameter bigger than the L infinity norms of V and H, then we have the truncations that we used, that we inserted into the system to handle the nonlinearities are never active. And so the solution to the cutoff system is also a solution to the original system. And the solution to the cutoff system can be proved to exist, for example, by some time discretization. Okay, so we have proved the existence of a solution. And what we did then is to do some numerical simulations for the 1D case, so in a simplified setting. And so what you have to imagine here is that we want to consolidate a beam, so something one-dimensional, which has a finite length between 0 and 1, for example. And here we assume that the active boundary is x equal to 0. So we are letting here the calcium, the lime water solution penetrate at x equal to 0. And to perform these numerical simulations, we have chosen some fictitious parameters with some simple value, because it would have been too complicated to perform an identification procedure with the data from the engineering literature. So this was just, this was out of the scope of our work. This was just to see if the behavior of the solution of our model was realistic in a sense. Okay, and then the final time t is determined by the number of steps that are needed to reach the equilibrium. And this is how the plots look like. Okay, so this is how they are obtained. So we started with some initial conditions equal to 0. And then in the time interval 0, t/4, we chose this S bar and H bar are the outer water saturation and concentration of calcium hydroxide. So this corresponds to the process of filling the structure with the water-lime mixture. And then at the time t/4, we started the process of drying. And this corresponds to switching this S bar again to 0 and H bar to 0 also. And then with this boundary data, we'll let the process run until the time t. And these are the plots. So as you can see, the dashed line corresponds to t/4. So when the process of filling stops, so you can see that since we've just filled the structure, the amount of water and the concentration of calcium hydroxide is maximum close to the active boundary, x equal to 0. So you can imagine here in the horizontal direction, we have the beam, which has to be consolidated, and these are the profiles along the beam of the concentrations and of the saturation. And then we have, of course, when we finish filling the structure, the concentration of calcium hydroxide close to the boundary and the saturation of water decrease. And the amount of water, which is essentially the integral of this curve is getting smaller and smaller. It's because for the water it can flow out of the domain. We are not imposing any unilateral boundary conditions like for H, for example. So the amount of water is decaying quite rapidly. But what is interesting to observe here is the behavior of the calcium carbonate, which is the product of the chemical reactions of the consolidant, because this gives you an idea of how the consolidation takes place. Because, okay, the dashed line is the time t/4. This is 3t/2, then 3t/4, and then this is at the final time, the continuous line. And you see that there is this kind of increase in the concentration very close to the active boundary. So the consolidation effect is not uniformly distributed inside the beam, but it really happens close to the boundary. And this is because okay, the water evaporates, it is removed, and line particles start to react, but there is a kind of partial back migration before the line particles really start to react. And so the consolidation effect happens really close to the boundary. And this is in line with the measurement in the engineering literature. And this is actually something that the engineers don't like, because they would like to have a uniform consolidation effect inside the beam. And so again, maybe with our model, we can try to help them in some way, try to optimize the procedure. Okay, so this was almost all, because, as I said, this was a kind of the first model in 3D for this kind of problem. So there is still space for improvement. And the first improvement that one should do is to include capillary hysteresis, of course, because what we assumed here was that between the saturation and the pressure, the capillary pressure, there is a functional relationship by means of a function f, which is increasing. But what happens in reality is that this relationship is of hysteresis type. So it's not just a function, it should be something like, yeah, it can be expressed really physically through a proper hysteresis operator. And the reason why this happens has to be looked for at a microscopic level. So why does this hysteresis effect happen? Well, it's a kind of combination of different effects, but maybe the most prominent one is the so-called bottleneck effect, and this is due to combination of two features. The first one is that the pore channels are not straight, but they have some, they're maybe thinner than larger, and so they're not straight channels. And the second feature is that the interface between the water and air is not flat, but it is curved, because the water tends to stick to the walls of the capillaries. And so what happens here is that, for example, in the inhibition phase here, in the inhibition phase, the interfaces must be repeatedly past very narrow pores. And for this, you need a higher capillary pressure. Well, instead, in the drainage phase, the interfaces must be pulled out from bigger pores. And so for this, you need a lower pressure. And this is, yeah, of course, due to the shape of the interface. And this is what is encoded in this, let's say, in this hysteresis loop here. Because yes, to reach a certain degree of saturation, you can observe that in the inhibition phase, a higher pressure is needed, while in the drainage phase, a lower pressure is needed. So this is exactly, this corresponds to this behavior at the microscopic level. And so maybe some future work should aim at including the hysteresis effects into the model. So substitute the function f with the hysteresis operator. Okay, but then there are also other possibilities for improvement. The first one is to include also the mechanical interactions, because of course the a fluid that penetrates in a porous medium produces deformations. And the same also when we have this crystal growth due to the carbonation procedure, then we have some deformations happening in the matrix. And then we also have some temperature effects because, as I said, the water is removed by evaporation, and this can happen also as a result of the chemical reaction because the chemical reaction releases heat. And so maybe it would be meaningful to include also the thermal effect inside the model. And then last point is that it would be interesting also to settle this identification procedure between our model and the measurements of the civil engineers, because as I said, when I showed you the numerical simulations, we didn't do that because it was out of the scope of this preliminary work. But yeah, in the engineering literature, there are a lot of data. So with identification procedure, I mean that, for example, they measure different quantities than the one that we have in our model, like the porosity. We don't have the porosity appearing explicitly in our model. We have this assumption on the permeability that decreases as the amount of calcium carbonate increases, but this is in some way something that replaces the assumptions on the porosity. But yeah, of course, the civil engineers measures the porosities in the experiment, and so it would be, for example, interesting to try to settle this identification procedure and explore a bit more in detail if our model can be relevant and really useful for them. Okay, in this I thank you for your attention.